Jai Hind to all. My name is Preeti Chaudhary. I am assistant professor in IT department at Ajay Kumar Garg Engineering College. So today I will discuss my next lecture in data structure, AVL. What is AVL and why we use AVL, types of rotation in AVL, insertion, how to do insertion in AVL, and AVL algorithm. So today I will discuss about the AVL tree. So before start AVL, I tell you about what is the drawback in BST. Okay. So according to this tree formation, here it is the BST. Let's suppose we take the example like this. Here, what is the main property of BST? BST have two property. It means left subtree of root is always less than root and right subtree of BST always greater than root. So according to this list, there is the right side BST. It means ki all this is the root part and this is a right side subtree, and this all elements in right side subtree is always greater. All elements are greater from root. So but according to this, if you want to search any number source to destination, like you want to 9 from this BST, so find out the number of here order of H complexity is increase in this scenario. Like if you want to search 9, so number of height of source to destination is 1, 2, 3, 4. So according to this, here the time complexity to search an element in a BST is order of H, where H is the height of BST. So in this scenario, BST have some drawback. Same things occur this part left subtree. Again, if you want to search any number from this left skew BST 1, so the same scenario occur here. Number of order of height also increase in this scenario. So so these are the problem in BST of searching any number source to destination and height also increasing here. So now next tree come which overcome the BST problem. So now I tell you about the AVL. What is AVL? Firstly, I tell you AVL is invented by 3 scientists. That name is GM Adelson, second one is Welsky, and third one is EM Landis in 1962. First, AVL. A for Adelson, V for Welsky, and L for Landis. So this is the surname of scientist. That name is invented by these 3 scientists. It is also called a height balance BST, because in a BST height problem is occur in BST, but in AVL we can remove this height problem. So also it is called height balance BST. Here each node is associated with balance factor. Balance factor, it means what is balance factor? Balance factor is height of right subtree minus height of left subtree. It means, let's suppose we take the example of BST and I tell you about how to find out the balance factor. Let's suppose this one is 4 and 5, 9, like this 6, and also here 3, and this one is 2. Now I want to find balance factor. The height of right subtree minus height of left subtree of each node. Here leaf node is this, because there is no child of this node, so it is called a leaf node. So according to this, 2 and 6 are leaf node. So here leaf node always balance factor is always 0. So 6 and 2 node have 0 balance factor. Now comes to 9. Next, according to height of right subtree, height of right subtree is 0. 0 minus 1 equal to minus 1. So 9 balance factor is minus 1. Now comes to 5. Here check again, this part is no child here, but height of right subtree, it means 1 and 1, it is 2. 2 minus 0. 2 minus 0, it means 2. It means here balance factor is 2. So if value of balance factor becomes 2 and minus 2, that time that tree unbalanced and need to be according to rotation. So now comes to the what is rotation and how it is used in AVL tree to balance to unbalanced tree. If a AVL tree become unbalanced after insertion of new node, then rotation operation are required. These rotation operation are basically 4 types. First one is LL rotation, also called a left rotation. Second one is right rotation, it means RR rotation, and third one is LR rotation, it means left right rotation, and fourth one is RL rotation, it means right left rotation. Here these 4 rotations are required to unbalanced tree to convert it into balanced tree. Let's suppose what is the LL? Now I tell you one thing more. LL and RR need only 1 times rotation, but LR or RL have required 2 times rotation. It means, let's suppose we take the example here. LL rotation, it means new node is inserted in a left subtree of left subtree in a main node. So these need only 1 time rotation. Like suppose we take the example here. You have root 5 and you inserted 4. Now you want to insert a new node, and this new node comes to left side of 4th. Now check the balance factor of this tree. So what is the formula of balance factor? Balance factor is height of right subtree minus height of left subtree. Okay, so find out the balance factor of each node here. So according to this 3 is the leaf node, so balance factor always leaf node is 0. Now comes to the second node is 4. Check height of right subtree is 0 minus height of left subtree is 1. So answer is minus 1. So minus 1 is also called, this tree is balanced tree. So no need to require any rotation here. Now comes to the third node. This is your root node. Now check again balance factor of this. So here height of right subtree, that is 0, and height of left subtree, it means 1 and 1 2, that is 3. So answer is minus 2. But minus 2 is the balance factor, not comes to in balance factor, it means it is the greater than minus 1 and plus 1. So now our given AVL tree is comes to unbalanced tree. So then we need rotate here. Now check which type rotation required in this scenario. Here check which type scenario will comes. For let's suppose we take the example here. It is this 4 is comes to the left side of 5, and this 3 is comes to the left side of 4. So here see LL rotation, or according to LL rotation need clockwise rotation here. Okay, clockwise rotation, or clockwise rotation also it need only 1 time rotation. Let's suppose it is rotate by clockwise. So output is 4 is root 5 will come right side and 3 will come left side. Okay, so now we'll check again. So this is the first time rotation called the LL rotation, or need only 1 time rotation here. Now check again balance factor of each node. Here this is a leaf node, so it is always 0, and again it is a leaf node, so it is always 0. Now check height of right subtree minus height of left subtree, so answer it is again 0. So now this scenario, according to this condition, this is converted like this. So now this after conversion, this tree is called a avial tree. Now comes to the second rotation, that is RR rotation, called a right rotation. Here again we need new node insert in this given tree. So check here, we check here 7, insert here according to this, okay, according to BST, because BST said right side subtree always greater than root. So 7 is greater than root and 6, so it will come right side of 6. Okay, so same thing agar if rotation is RR, so need only one time rotation here. So now check balance factor of each node here. According to this, 7 is your leaf node, so according to leaf node, balance factor always 0 of leaf node, so it is a 0. Now we'll check 6, node 6, again right side subtree, height of right subtree 1 and height of left subtree is 0 equal to 1. Now comes to 5, again check height of right subtree means height is 1 and 1, it is 2 minus 0 equal to 2. So here balance factor value is 2. If your balance factor value is 2 or minus 2, it means your tree, avial tree, is not a balance. So now need to any kind of rotation, but according to this scenario we need right rotation, because it inserted right direction, so need a right rotation. Again if your rotation is right or left, then need only one time rotation. So according to this, rotation is anti-clockwise. Okay, so according after rotation, your tree will come like this form. So this tree, now check again balance factor of each node. This is a leaf, it is leaf also, so sorry, balance factor always 0. Now check height of right subtree minus height of left subtree is 1 1, so answer is 0. So according to this is called a right rotation. And now this after conversion, this tree is called a avial tree. Now comes to the third type rotation. According to third type rotation means left right rotation. If you required in your given tree left right rotation, then it needs 2 times rotation. Okay, 2 times rotation means if your rotation is LR, it means first rotate is LL, then rotate is first rotate is RL, then rotate is LL rotation. So according to this, check again what balance factor here. So it is a leaf node, so balance factor of each here is 4. Now check right height of right subtree here 1 minus 0 equal to 1. So there is no need to any kind of rotation required here, but then I will come next node is 5 and check again the balance factor of 5 is here. So right side subtree is 0, height of right side of 5 is 0, 0 minus 1 and 1, it is 2. So answer is minus 2. It means if your balance factor is minus 2, so same condition occur here. If balance factor is minus 2, so then need to required LR rotation. How? Check. 3 comes L side and 4 come is right side. So there need LR rotation. Now how to LR rotation work? Firstly convert is anti-clockwise, only these 2 points. Here see 5 converted into 4 means just need is same condition. this one is one rotation required is this. Now converted your balance, but this is not a balance AVL tree because here need on one more rotation required here. Now it is comes to will come this rotation here LL, or in a LL rotation need clockwise. So now comes to 4, 5 and 3. So here need 2 times rotation. First one is anti-clockwise, means this is the interchange, not interchange, and rotate also here 4 like anti-clockwise. In anti-clockwise 4 will come upper side and 3 will come right side of 4. Now comes to this is converted into LL rotation, but in a LL rotation need to one time rotation. So and this is a anti-clockwise, sorry, clockwise, and in a clockwise converted into like this. So this is a converted AVL tree, and this is a totally AVL balance AVL tree. Now check the balance factor again of this. This is the leaf node. Again leaf node is always 0, and this is also 0 because right side 1 minus 1 equal to 0. So now this after conversion this tree is called a balance RL rotation. RL rotation means right left rotation. New if you want to new insert the node is left side, but here already inserted according to this scenario. Now it is also the RL rotation, so need to 2 times rotation required here. So again check the scenario here, same things. It is right and it is comes to left, so it means according to this RL rotation. But check it is balance factor ki need RL rotation or not. So same things here. Check the balance factor, it is 0. Here balance factor is 0 minus 1, it minus 1, and again here balance factor is 2 minus 0 equal to 2. It means this part will come unbalanced. So need to required. So according to this is according to required the RL rotation. So RL rotation required. So firstly we here need to 2 times rotation in this RL or LR rotation. Got it? And according to this RL or LR rotation, check converted into firstly RR rotation. Firstly converted into this portion clockwise direction. After it will come RR rotation, then again rotate by anti-clockwise. Okay, so check again here. 5 is this, now converted into clockwise, so 6 will come here and 7 will come here. Now it is a right and right rotation. Got it? Got it? A right and right rotation need, it is a one time rotation here, and this one time rotation is anti-clockwise. Okay, according to anti-clockwise this will come 6 and this one is 7. Okay, now check again these things. Find the balance factor of each node. Same 5 and 7 is leaf node, so balance factor always is 0 and 0, and 6 have same types of height, right? Height of right subtree minus height of left subtree, it means 1 minus 1, so it will become also 0. So here these 4 types rotations are required: LL rotation, RR rotation, LR rotation and RL rotation. In same types rotation like LL or RR rotation, if you rotation required LR or RR rotation, so need to 2 times rotation. Okay, so according to this, if your balance factor is value is 0, -2 and +2, means they need the your tree is unbalanced and need to convert into balanced tree using these 4 rotation: LL, RR, RL or LR. Got it? Now will comes to the construct the AVL tree. we take the example also A, Z, B, X, Y, C, D. But before I explain this example, I will take the simple example for AVL construction. After that, I will explain you by this alphabetically example. So here, according to this, we take the value here 1 to 10. Simple value, we take the 1, 2, 3, 4, 5, 6, 7, 8, 9, and this one is 10. Okay. So before, this is the second example, and now I will tell you the first example. This is a numeric example. Firstly, I tell you this example constructed AVL by this example. After this example, I will explain by alphabetically. Okay. So according to this, firstly I tell you AVL tree. AVL tree also follow the BST property, and BST property have two types property. First one is right side subtree, all all element of right side subtree is always less than to root, and left side all element is always less than to root, and right side always greater than to root. So this is the main property of BST. So AVL also follow this property AVL, but there is one thing, if your balance factor is value is 2 and minus 2, then need to rotation, and after rotation this tree is converted into AVL tree. Okay. So according to this, here we take the example 1 to 10. Now we convert construct a BST using a AVL tree. So this is your first node, and this is called a first is root node. Now comes to the 2. The 2 where will come, left or right, because 2 is the greater than 1, so it will come right side. Okay. So it will come 2. Again check the balance factor of, here the balance factor need in all addition, all insertion. If any number is insert, then check balance factor of all element. Okay, in each condition, in each step. Okay, now we will check here, this one is 0. Okay, and because it is a leaf node, and according to this here 1 is this one. So again, because right side 1 is this one, and this one is 0, so यहाँ जाएगा 1 minus 0 equal to 0. So no need, it will be 1. So there is a balance, no need to require any kind of rotation. Now we'll come to 3, and 3 inserted into here. 3 inserted in here, and now check again balance factor and update the last balance factor of each node. So this is the 0, and according to this, right is 1 and left is 0 equal to 1. According to this, right is 2 minus 0 equal to 2. So balance factor is 2 is here. So need to rotation. Which type rotation are required here? Right rotation. So according to right rotation here, need to anti-clockwise rotation are required here. So it will converted into 2, 1 and 3. And check balance factor again here, 0, 0, and it will come 0, 0 again, and it will come again 0, because height of right subtree minus height of left subtree, it means 1 minus 1 equal to 0. So now we'll come to the next number, insert here 4. Okay, according in this balance tree inserted. So now again inserted here 4. Okay, so no need. So again update all element balance factor here, it is 0 again according to this 1, and here check the again 0, and 2 minus 1. The 2 minus 1 equal to again 1. So no need to, balance factor is 1 here, all in each 0 and 1. So no need to require any kind of rotation here. Now we'll come to the next node, insert here, that is 5. Okay, now it will come to 5. Now check again balance factor and previous balance factor updated of each node. Here and check that it is 0, and according to this is 1, and according to this is 2, because height of right subtree is 2 and left subtree is 0. So 2 minus 0 equal to 2. So there again required the what? Right rotation. So right rotation need to anti-clockwise. Here check 2, 1, sorry, anti-clockwise, na? So it is a 4, now it will come 3 and it will come 5. Now check again the balance factor of each node, same things, 0, 0 and 0, and this is a 0 and 2 minus 1, it was 1. So now this balance factor is value is 1 and 0. So this is this tree is a AVL tree, is mean totally height balance tree. Now it will come to the 6 inserted here, same condition. Now it is the inserted, and check again balance factor here, 0 and this one is 1 and this one is 2 minus 1, 1. Now again check 1, 2, 3. 3 minus 1, it means 2. If it is 2 means here need adjacent 3 node. And which type rotation are required? Here required R rotation. Okay. According to RR rotation required anti-clockwise. Check here, according to BST condition, 4 comes to top, 2 here left side, and 1 is left side of 2. Now it will come 5 and this will come 3. Now the problem is, according to this scenario, one problem is occur, 3 is left. 3 is left from this tree. Now check according to BST 3 where will come. So according to this, 4 is the root, so 3 always will come left side, because 3 is the less than root, it will come. Now check here, 3 is the less than greater, so it will come right side of 2. Okay, so in this way these numbers we can insert one by one, and at the end we find the balance tree, height balance tree using AVL tree, using types of rotation. So in this chapter, in this session, I will discuss. I have discussed some points. First one is what is AVL tree, why we need AVL tree, and some drawbacks of BST. After how to construct AVL tree and required different types of rotation, and these rotation are how to work. So in this session, I have discussed these points. In my next lecture, I will discuss about B tree. Thank you so much.